Hey everyone, this is Daniel for Rock the JVM, and this video is on type-level programming in Scala. We're going to do an overkill tic-tac-toe with the type system in Scala. This video is inspired by a series of tweets that I saw on my timeline a couple of weeks ago, praising the TypeScript language for how powerful its type system is that you can do type-level programming on it. So I tweeted, hey, do you want a TypeScript versus Scala duel on type-level programming, at which somebody replied, hey, TypeScript just owns Scala for this tic-tac-toe written at the type level. So besides the quicksort on types that we did almost a year back in Scala 3 at the type level, which you can find here at Rock the JVM, I wanted to score a little point for Scala by doing this tic-tac-toe in a little sketch in this video. So the assumptions here are that you obviously know the fundamentals of Scala, that you know how Scala 3 givens work, because we're going to rely the type inference on the given resolution. And if you want to make the most out of this video and you want to flex these type system muscles, I recommend that you write code with me, and whenever you need to refresh your memory or use these sort of skills, just refer back to this video or to the written form of this video at the blog with the link in the description. All right, so without further ado, let me switch back to my little development environment where I have a little object with a main method, and we're going to do the tic-tac-toe here at compile time from scratch. Now, in order to run a tic-tac-toe, we need to represent it, and we need to represent it at the type level. So we need some building blocks in order to represent the tic-tac-toe board. First of all, we need to represent numbers. So numbers will be represented at the type level. I'm going to represent that as a trait. I'm going to call this nat for natural. And we're going to represent not values, but types that extend this nat thing. So I'm going to define a class called, I'm going to name it _0, and this extends nat. So this is the number 0 at the type level. So the type that represents the number 0. And I'm going to define a little class that I'm going to call successor, or suck with a 2c, and I'm going to have an n, which is a nat, and this extends nat. This is going to be the successor of any natural number that extends nat. And with these two natural representations, we've essentially covered the entire natural spectrum, because even the number 2023, the year that we're recording right now, this is a successor of 2022, which is a successor of 2021, which is a successor, and so on and so forth. So the number 2023 is the successor of successor of successor of whatever of successor of 0 ultimately. So with 2023 different levels of parentheses here. So you can represent an arbitrary large natural number here. Okay, now I'm going to define some type aliases so that we can work with them more easily. I'm going to have a type _1, which is successor of _0, and I'm going to use 2, 3, 4, and 5, let's say. So I'm going to have 2, 3, 4, and 5. Okay, now the types 1, 2, 3, 4, I'm going to copy them and I'm going to place them here to establish the right relationships. So 1 is successor of 0, 2 is successor of 1, and so on and so forth. I'm going to just keep these 5 for now. So we have numbers. Then we need to have the players. So players and cells in the tic-tac-toe board. I'm going to define the type player as the string x or the string o. In Scala, we can do literal types as well. And I'm going to define a type cell, which is either player or an underscore. So this is a regular cell that will occupy a position in the tic-tac-toe board. So this is just at the level of the types. Okay, now the tic-tac-toe board can be represented at the value level, so in regular values, as lists of lists or arrays of arrays. However, at the type level, every single array will need to be represented in the form of the types that it will quote-unquote contain. So I'm going to define a trait that will denote a type level list. This is, by the way, a type that can be found in other libraries in the Scala world, for example, shapeless. And this H list that I'm just defining here is a higher level list, a type level list. And I'm going to define a linked list, which is denoted by this little trait at the type level. I'm going to define a class called, let's call this h_nil, which is the empty list. So empty list with a quotes. And this extends h_list. And then I'm going to define a class. I'm going to call that colon to denote the same kind of notation that the regular list in the Scala library also has. So this class colon will take a value, which is the head, but the head is a value as at the type level, so it's a type. And then the tail, which is an hlist. And this extends hlist. And with these two representations, I've essentially covered the entire hlist representation because this class, colon, can be arbitrarily large or arbitrarily typed because you can put any sort of types into this list. And because I'm using this class, colon, I'm going to use that infix, just so that you can use that in infix notation. Then I'm going to define the board, so I'm going to use a type board as an hlist, because you can't define a list of lists because this hlist can be heterogeneous and the h type itself can also be a list. So you can define a list of arbitrary depth of arbitrary types. So the type board is an hlist essentially. I'm going to define a type, let's say empty row, which looks something like this. I'm going to use the underscore and then another underscore and then another underscore, and then the hnil, which is essentially a non-empty list where the first element is the type underscore, and then the rest of the list is another non-empty list with the underscore as the head, and the tail of that is another non-empty list with an underscore as the head, and finally we have an hnil at the tail of that, so we have 3 sets of parentheses, 3 sets of angular brackets inside. So this is the equivalent notation of an empty board. Now the empty board is built out of 3 empty rows. So the type empty board is going to be empty row, and then empty row, and then empty row, and then an hnil. So this is essentially a list of 3 lists, which are themselves built out of these underscores. All right, so this is the kind of types that we're going to work with. Now, the whole point of deciding what happens to a tic-tac-toe game after a move, or deciding who wins given the board of a tic-tac-toe, is all about satisfying predicates. That is, satisfying connections or relationships between types at compile time. And the way that Scala does it is by inferring given instances for particular types. For example, I'm going to start slow. Let's assume that for this little trait for which we have no APIs, we would like to implement a type that decides what length an hlist has. I'm going to define a trait called length that given a list, which is an hlist, and an n, which is a natural, we say that a type length with L and N exists if the length of this list is equal to n. So length of L and N exists if the length of L is n. That's the whole meaning of the type length ln. And the way that we make sure that this length L exists is by making the compiler create given instances for us. For example, I'm going to define a given value. I call this 0 length. This is a length of hnil and the type underscore 0. And I'm going to say with parentheses because that's how the compiler knows that this thing will be instantiated. So we say that there is an instance of length for hnil and 0, or in other words, the type length with hnil and 0 exists. In other words, the length of hnil is the type 0. So notice that this type length for L and N is essentially a predicate that establishes a relationship between an hlist and a natural by the existence of the instances of these types. So we call this an axiom because this is the basic predicate that the length of an empty list is the number 0. I can create another given that relies on existing givens to create new instances of length for particular types. So I'm going to say, let's call this length inductive, which takes a head, a tail, which is an hlist, and the head and tail will comprise a new list, and an n, which is a natural. And we say that if we have, using a using clause, a length of tail and n, then the compiler will instantiate for us a length of h and t, and then the successor of n. So in other words, if the length of tail is n, then the length of something concatenated with a tail is the successor of n, or n plus 1. And with this, we've defined all the possible correct predicates for the length of a list. Now, for those of you who have ever programmed in a very, let's say, esoteric and also quite old programming language called Prolog, this is essentially what we're doing. We're essentially creating constraint satisfaction rules. So this essentially allows the compiler to build instances only for those types that satisfy the kind of requirements that we create using the using clauses here. So here in main, I'm simply going to define a val a, let's say, as summon, which essentially fetches the implicit value or the given instance for a particular type. I can say length of h nil and 0, and if I save and if I try to run this code, obviously we're not going to see anything being printed to the output, but if the code even compiles, then we have the matching or the correctness of the predicate length for h nil and 0. If we say length of h nil and 1, which is an incorrect predicate, obviously the length of an empty list is not 1. If I try to recompile this code, we will not be able to compile the code. So if I do Command-Shift-9 and if I trigger the compiler, notice that we get a compiler error saying no implicit argument of type whatever, which is to say that the type length h nil and 1 doesn't exist. So the predicate of h nil's length is equal to 1 is false in our jargon. I can do something else. For example, I can say the length of the empty board. So empty board must be _3. If I compile this code, then the code will compile because the length of an empty board is successor of successor of successor of 0. So notice that the code compiles successfully. If I do _4, then the code will not compile because the length of the empty board is not 4, it's 3. So if I trigger the compiler, we'll get into the same kind of compiler errors. So this is the kind of technique that we're going to use to define properties of a tic-tac-toe and whether a player wins or loses. But obviously we need to have some sort of standard library to use so that we can define the necessary predicates. So let's solve the problem of who wins in a game of tic-tac-toe. This is a standard interview question that's usually solved by processing arrays, and this tests foundational computer science concepts. But obviously we're going to take it 10,000 steps further at the type level. So in order to determine who wins in a game of tic-tac-toe, we need winner by row, we need winner by column, we need winner by diagonal 1, and winner by diagonal 2. Did I just say diagonal? Whatever. Okay, so we need to solve all of these problems so that we can decide who wins in a game of tic-tac-toe. I'm going to take this in turn. Winner by row. Okay, how do we decide if a player is a winner by row? Well, a winner is by row if the entire row has the same values. Well, in order for us to do that, we will need to define a trait, or rather predicate, whether an array or a list has the same values. So same values for a list, which is an H list, and the value V. That is to say that if the same values for L and V exist, then the list L has all the values equal to the type V. That's the general predicate that we're going to do. Okay, let me define a given. So I'm going to say SV basic, and I'm going to define an axiom for an empty list. So I'm going to say for every type V, then the compiler will be able to create a same values for the H nil and V. That is to say that the empty list has all the values equal to V, which makes sense because this one has no values. And so they're all equal to V in a sense. Then I can build an inductive one. So I'm going to say SV induction or inductive that takes a T as a list, so H list, as a value V. And assuming that there is the same values for T and V, so using same values with T and V, then the compiler can build the same values for V and T with V. Think about it. If you have a list that has all the values equal to V, then another list with V as its head with that rest of the list also has all its elements equal to v. If you want, you can pause the video to process that. So if the type t has all the values equal to v, then if I put v at the front, then I can also build the same values for this new list with the value v. Okay. Now, if we want to test whether a player wins a game of tic-tac-toe by considering just the rows, I will have to consider all the rows in a board. So I will define another trait. I'm going to say wins by row, which takes a type B, which is a board, and let's say winner, defined by W, as a player. Remember, the player is X or O. Okay, so we have wins by row. The trait wins by row says that the board B has been won by player by considering any of the rows in the board. Well, in order for us to do that, we need to consider all the rows in the board. So I'm going to define a given. I'm going to say wins any row. That takes a row as an H list. And the rest of the rows, I'm going to call this RT as an H list. So this is a list of rows. And P as a player. And I'm going to say using same values for R and P. So if all the values of the row R are equal to P, then the player P has won the entire board. So I'm going to build a wins by row where the board is R concatenated with RT. So this is R concatenated with RT and the player P. That is to say, if all the values in the row R are P, then player P has won in the board R with whatever other rows the board might contain. Okay, that's one. Another possibility is that the player P might win the rest of the rows, not just the row R. So I'm going to say given wins any row 2. Actually, let me call this given wins first row. So wins first row, and I'm going to call this given wins any row. For R as an H list, RT as an H list, and P as a player. And I'm going to assume that the player P wins the rest of the rows, not just the row R. So I'm going to discard the row R because the first axiom considers that. And I'm going to assume using wins by row with RT and P. And this is going to be a wins by row with R concatenated with RT and P. In other words, if the player P wins any row in RT, then the player P has won the entire board, R and RT. So I'm going to assume that this wins by row holds true for a particular board, and we can test that. So I'm going to say value A is summon of wins by row, and I can put some rows inside. I'm going to use this one. So let me add some parentheses. So this one, and then this one, and then this one, and then H nil. This is a board. And I'm going to assume that the player X has won. This code will not compile. Let me arrange my code a little bit. So wins by row with this little thing, and then this little thing, and then this little thing, and then H nil, and the player X. Okay, so this is my 3x3 board. Obviously, it's empty. If I recompile this code, the code will not compile, obviously, because the X value doesn't exist here. So the code doesn't compile because the implicit value was not found. But let's try marking our territory with X's. So if I do X's on the first row, the code will magically start to compile because the first row contains just X's. Let's see. Okay, so we have the code compiling. If we swap these rows around, so if we swap them and put the X on the second position, the code will still work because the rest of the rows are still being considered by this other axiom. And if I do this is won by the letter O, we are going to obtain a failure, so the code will not compile anymore. All right, so the code doesn't compile as expected. So even if I have an underscore and an X here, obviously the code will not compile anymore because no single row has just X's. Alrighty, cool. So we have a wins by row. Okay, I'm going to comment this out, and we're going to go forward with winner by column. The winner by column is a little bit more complicated because now we need to map all the columns in the board and then subject every column to the same values predicate. The mapping of the column is the complicated bit. So I'm going to define a little trait to map column. So I'm going to define a trait called map column. Okay, map column will take a B as a board, and then the column index, which is a natural, so I need to somehow take these two elements, or three elements, like this, and combine them into a list. That's going to be a problem. So I'm going to have a column index, which is a natural, and then the output, I'm going to say O, which is an H list. So in other words, what I'm saying is that the map column type BCO exists if for the board B, at the column index C, the list O is the appropriate column representation of that defined as a list. Now this is going to be a little interesting because I now also need to create a little quote-unquote API or utility function to take the nth element out of a list. So I'm going to define a take nth element. Okay, let me do the take nth element. So a trait take nth that takes a type argument L, which is an H list, a natural N, and this is going to be the index at which I'm going to extract the element V. So we say that the trait take nth L and V exists if for the H list L at the index N, the value V is going to be returned. Again, I'm going to define that as axioms. So I'm going to have a given, let's call this Tn, that's for take nth basic. And I'm going to have a T as an H list and a V. And I'm going to return a take nth for the value V combined to T at index 0 and the value V with whatever. Okay, what does this mean? That if you want to extract the element at index 0, first of all, the list must not be empty. And so it has to be expressed in the form of head, colon, colon, tail. Besides that, the head must be equal to the value that's being extracted. So V must be equal to V here on the right-hand side. Okay, so this is the basic axiom if you want to take the first element out of this list. Let's assume that you want to take an element at an arbitrary index. So I'm going to call this Tn inductive. I'm going to consider an H, which I'm going to discard. So an H, a tail, which is an H list, an index N, which is a natural, and V, the value V that's going to be extracted, obviously at the type level. So I'm going to say using take nth for TNV, that means if I extract the nth element out of T, and that is V, then I'm also going to be able to say take nth with H combined to T, and the index is going to be successor of N, and the same value V. Think about it. If you have the list 1, 2, 3, 4, 5, 6, and you want to extract the fourth element out of it, so the index 3, N is equal to 3, the value is going to be 4. Okay, we rely that on the fact that we can also extract the element at index 2 out of the smaller list. So 2, 3, 4, 5, 6, N equals 2, V is still equal to 4. Again, I can say 3, 4, 5, 6, N is equal to 1, V is equal to 4. Then we have 4, 5, 6, N is equal to 0, and V is equal to 4. At this point, we get into the basic axiom, so the compiler figures out that there is a take nth for these types, 4, 5, 6, N is equal to 0, V is equal to 4. So it can synthesize a new given for this list, N equals 1, V equals 4. So it can synthesize a new given called take nth for this list, N equals 2, V equals 4. And so it can synthesize a take nth for the one that we were interested in. So this is how the compiler works. It can synthesize values up to the point where it cannot synthesize any more givens. And if this branching or if this given search or given resolution algorithm stops creating new potential values for our resolution, then the code will simply not compile. If it simply finds just one given, then it will construct the dependent givens of this resolution dependency. So I hope this makes sense. So this is take nth. Now, in order to map the column, so let me put this comment right next to the little trait, I can also define some axioms. Let's say given, let's call this map column basic. Okay, let's consider a row, which is an H list, the column index, which is a natural, and the value v. And I'm going to rely, let me add a parenthesis here. So I'm going to say using take nth with RCV, this is going to be a map column with R and H nil, the column index C, and V to H nil. Okay, this deserves some explanation. Let's assume that this board is a list of lists or a matrix. Now, how do you map the column of a matrix? Well, you first map the column of a matrix by mapping the column of a degenerate matrix, which is essentially a single row and nothing else. So a matrix of one row times n columns. Now, how do you map columns of matrix 1 times n? Well, you'll simply return a single value, right? So if you have a matrix of dimensions 1 times n, you'll essentially get a single value. Well, essentially what we're doing here is if we can find a take nth for RCV, we're simply returning that v, that single value, into the appropriate quote-unquote column, which is v with h nil. This is essentially what this MP basic matrix predicate does. Now let's extend that to larger matrices. So I'm going to say matrix of m times n. Well, a matrix m times n first needs to take a single value from its first row, and then, so take first value out of first row, and then map column for the matrix which is one row less, so m minus 1 times n, and concatenate that first value with the rest of the result. So recursive given resolution. So I'm going to say given MP inductive. Okay, let's take a row, which is an H list. The column C, which is a natural. Let's also have the rest of the rows, which is an H list. Okay, C is a nat. Then we have the value V, which is a value in this row R. And the rest of the values, I'm going to call this VT for VTail, which is an H list. Now, I'm going to assume, so I'm going to say using. First of all, I'm going to assume that the nth element out of the first row is V, and the map column for the rest of the matrix is VT. So I'm going to rely on take nth for RCV, and map column for the rest of the types, so RTCVT. This is going to be a map column for the combined matrix, so the first row combined to the rest. This is R and then RT. The column index remains the same, and the value is going to be V, the first row's item at column C, combined with the rest of the values, VT. So this is going to be, get out of my way, V and VT with that little token. Okay, so we're mapping the column of the board by returning that particular column at index C. Okay, now, if we are doing winner by column, then we need to map all the columns of the board. Okay, let me define a little trait. I'm going to call this wins by column up to a particular index. So I'm going to have a B as a board, a column index, which is a nat, and the winner is a player. So this predicate says that the player wins on this board by considering all the columns up to non-inclusive this particular index. This is what this trait means. So I'm going to define the axioms as well. So let me define a, let's say, wins first column, which takes a B as a board. And I'm going to map the first column of this board to another type. I'm going to use L here as an H list, and W as the player, the winner of that. And I'm going to assume that we have a map column with B and the index 0 maps to L. So the first column is L. And I'm also going to assume that all the values in this list L that I've just mapped are equivalent to W. So we have same values for L and W. And if we have those, then I'm going to have a wins by column up to B. And I have to be careful here with the index C. I'm going to use _1 here. That is because the first column was the winner, so I'm going to consider that the winner won the board up to column index number 1. I said non-inclusive, so W, with the little token here. So the first column is this wins by column up to _1. We're going to generate predicates of wins by column up to for all numbers up to the length of the first row. So that's going to be a little complicated. We're going to take it step by step. So I'm going to have another given wins any column, and I'm going to have a B as a board, a C as a nat, so board, a column index C as a nat. Then we have L as an H list, which is the column mapping of this index from the board, and it maps to L. And the winner is W, which is a player. Okay, then if I have a map column, so if we have map column that from the board B at the column index maps to L, and then I have same values for L and W, then I will synthesize wins by column up to B, C+1, which is successor of C, and W. That is to say, if the player W won the board at this exact column index by satisfying these predicates, then I'm going to generate an instance of wins by column up to successor of C. So I mentioned that the index here is non-inclusive. So with this little thing. Or if the player W won the board up to C, then I'm also going to consider that this board was won by the index C+1. So I'm going to say given wins any column, I'm going to say column 2 with B as a board, C as a nat, and W as a player. And I'm going to assume that this player has already won. So wins by column up to, and I'm going to have up to B, C, and W. Then the compiler will generate wins by column B, successor of C, and W. So if the player has already won by the column C, then this player has already won by column C+1 as well. So essentially what I'm testing is all the column indices at the board that may be won by this player. Finally, I'm going to define a trait. I'm going to say wins by column with B as a board, and W as a player. Now the only given that I'm required to say wins by column is to test all the indices up to the length of the first row in the board. So I'm going to define a given. Let's say wins by any column. And I'm going to have, let's say, the first row. So let's say FR as first row, which is an H list. Then we have the rest of the rows, RT as an H list. Then we have the winner as a player. And let's assume that the length of the first row is L. So L is a nat. Now I'm going to have to add the predicates. So I'm going to say using length of the first row must be L. And we also need to have a wins by column. So wins by column up to. And the full board is the first row concatenated with the rest of the rows. So I'm going to say FR with RT. Then the column index is L, so up to the column index L, non-inclusively, of course. And the player is W. Then I'm going to generate a wins by column with the board FR and RT, and the winner W. Cool, so this is essentially it. This is the wins by column where I'm essentially testing all the indices 0 until L, And I'm going to make the compiler generate a potential predicate for me for all the columns up to L. Let me test this. So I'm going to run the same code as before with, instead of wins by row, I'm going to use wins by column this time. So we have a summon with wins by column with this board and X. Obviously, this code will not compile because there is no column with all the values equal to X. So I'm expecting this compilation to fail. Okay, so we have a failed compile. Let's take one column instead. So I'm going to have X on, let's say, the second column, and I'm going to test all the columns just to be sure. So let me compile this again, and at this point, the code should compile. So we have compiling, finding implicit values. Okay, so we have a compilation success. Let's test the column number 1 as well. The compilation should be successful. Okay, so that was one. And let's also test the third one. We should be getting into a similar situation. Okay, good. So if I cut one X out and I put an underscore, then the compilation will fail again because there is no column with all the values equal to X. Okay, good. So we have the wins by column predicate as well. Cool, so we have wins by row, wins by column. Let's do winner by diagonal 1. By diagonal 1 means that I have to map the diagonal of the board. So I'm going to have a trait called diag1 with B as a board. And I'm going to say I as a nat. This is going to be an index at which I'm going to extract a value. And the diagonal D, which is going to be an H list. Here's how I'm going to extract this diagonal. Given the fact that I'm already at index I, I'm going to try to extract the next value out of a given row. So I'm going to have, let's say, given, I'm going to call this diag1 basic. Given a row as an H list, and an N as a natural, and a V, the value that I'm extracting here, I'm going to assume that if the length of R is equal to N, and I can take nth at from the row R at the index n minus 1, and we have the V, then the diagonal is just the list containing V. So I'm essentially extracting the last row of the entire board. So if we have like a 3x3 board here, the element at the diagonal, at the first diagonal, is this one, the very last element. So I'm going to essentially take all the elements one by one in reverse order. The way that I'm going to do that is because I don't have access to a difference operator between natural numbers, I'm going to say using length with R and successor n, so that this little successor n is my length. Then n minus 1 is the n type that I've added here in the type argument. So with length R, L, and successor of n, and take nth with R, N, and V. So R, N, and V, and the n is the length minus 1. Okay, so successor n is the length, and n is the length minus 1. So let's call this L, and we have L minus 1, and this L minus 1 is equal to the n type here. Then we have the diagonal is equal to the value V as a plain singleton list. So I'm going to make the compiler generate a diag1 with that single row, so R concatenated to H nil. Then we have the index at which I'm extracting it, which is n, and the value V. The value V is going to be an H list, so I'm going to concatenate that to H nil. So the singleton list, obviously with the little token. Okay, so the diag1 basic extracts the last element out of the last row. So assuming I have that, I can create new givens. So I'm going to have diag1 inductive, considering a row which is an H list, the rest of the rows which is an H list, and which is a nat. The value V that I'm going to extract out of this particular row, so V is going to be a plain type, and the rest of the values that's already been extracted out of the rest of the rows, so this is going to be an H list. And I'm going to assume the existence of a diag1 of the rest of the rows, successor of n, so that is the index n plus 1, and the rest of the values that I've already extracted. And assuming that I can also extract the nth element out of the first row, which is v, so I'm going to say take nth, which is rnv, I'm going to make the compiler generate a diag1 with the first row concatenated with the rest of the rows, n, and the value v concatenated with the rest of the values. So imagine this. If I am at the first row and I've already extracted the rest of the diagonal elements out of the last two rows, then all I have to do is extract the first element and combine them to the last elements. Let's demonstrate that with a simple example. So I'm going to have a val a as a summon with a diag1, and we need to have a board. So diag1 needs to have a board. I is a natural, which is a 0 in my case. And the diagonal is underscore, underscore, and x. So I'm going to have underscore, 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 and then an x, obviously with an h-nil. I think I have too many underscores, so I have 3. I need to have just 2. Okay, let's save and let's compile this. If the code compiles, then this list is a proper first diagonal of the first board. Now, diag1, not enough type arguments. Not enough type arguments. I think I've misplaced something. So diag1 has, yeah, h-nil. I think I cut the h-nil out. Okay, so this is the board. This is the first type, which is the 0, and then the final list. Let's see. Let me add a comma here. Let's compile this again, because I added the comma. Okay, and the code finally compiles. So that was my fault because I didn't specify the types properly. So diag1 with this little board, underscore 0, so starting at index 0, I'm going to obtain this first diagonal. If I add the O here, then the O will be reflected into the first diagonal as well. All right, so let's wait a few seconds for the compiler to validate what I've just written. All right, so this is how the first diagonal is being extracted. Now, once the first diagonal has been extracted, winner by diagonal 1 is easy. So let me make a trait called wins by diag1. That takes a B as a board and the winner as a player. Cool. Now, the winner by diag is going to be a given. Let's call this wins by diag1, that given a board, so B as a board. Let's call this D1 as an H list because I'm going to extract it. And the winner is a player. Assuming I can extract diag1 with B underscore 0, so starting at index 0, and I obtain the diagonal 1 D1 as a list, then same values throughout D1 as the player W, then I'm going to make the compiler generate for me a wins by diag1 with B and W with a little token. Cool, let me try it out. So I'm going to create my first example where I'm going to simply say wins by diag1. And let me compile the code, and this code will not compile because x does not win by a diagonal. Okay, so the code doesn't compile. But if I make the first diagonal equal to x, so I'm going to say x, 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 and I'm going to place underscores everywhere, maybe a 0, whatever. Cool. Let me compile the code, and the code should compile at this point because the diagonal was successfully extracted. All right, so the compiler is happy with my code, therefore x1. Cool, let's do diagonal 2 this time around. We need to do the same thing. We need to extract diagonal 2, and then we're going to have a very similar given for wins by diagonal 2. So I'm going to have a trait, diag2, with B as a board, I as a nat, and D, the diagonal, which is an H list. And the way that we are going to build our axioms will be very similar to diag1, except for diag1, we extracted the last element out of the last row for the first diagonal. But for the second diagonal, we need to extract the first item out of the last row. This is how we're going to build it. So we're going to extract the first item out of the last row, the second element out of the second to last row, and so on and so forth up until the first row where we have to extract the last element. Okay, so let me define a diag2 basic that takes a value and a t, which is an h-list. The whole point is that this last row is the value v concatenated with the rest of the row, which is this little t. And this will bring us a diag2, where the b as a board will just have the last row, which is vt, the last row, and h-list. Not h-list, but h-nil. And then we have the index 0 and v with h-nil. And obviously with a little token. And the inductive will look something like this. I'm going to say diag to inductive. That will take a row, which is an h-list. The rest of the rows, which is again an h-list. The index I, which is a natural. Then we have the v, which I'm going to extract out of the row r. And the rest of the value is vt, which is an h-list. And I'm assuming the existence of a diag2 with the rest of the list, the index I, and the rest of the values. And assuming I can take the element at index I from the row r, and that is v, so take nth. So take nth from r, and I need to be careful with the indices here because I need the successor of I. So successor of I, and I will obtain the value v here. Then I'm going to make the compiler create a predicate for diag2, and the board is the row combined with the rest of the rows. And we have successor of I, the next index. And the values are going to be v with vt. So the index I is the index up to which I'm building the diagonal d out of this board. This is essentially what the I means. So if I can extract the I plus 1th item out of the current row, and given the diag2 that I've constructed up to index I so far, then I can construct a diagonal up to index I plus 1 from the composite board, returning the composite values. This is what diagonal to extraction means. Let me define the winner by diag2, and then finally we're going to win the entire game. So, trait wins by diag2, b as a board, and winner as the player. Okay, there's only one axiom there, so I'm going to say given wins by diag2. And now we need to be careful because we need the final index by which we can iterate, which is the length of the first item, the first row in the board. So I'm going to have a row, which is an h-list, the rest of the rows, which is an h-list, the length of the first row, which is a nat, then the diagonal, which I'm extracting, which is an h-list, and finally the winner, which is a player. Okay, I need a bunch of predicates here. First, the length of r must be equal to L. So using length RL. Cool. Then I need a diagonal true extraction out of the entire board, which is a diag2 with the board is RRT. Then the maximum index is going to be L minus 1. So I need to have L minus 1, something like this. But I can't use L minus 1, but rather I'm going to use n here as a nat, and L minus 1 is going to be n here. And the L is going to be successor of n. So I'm doing a variable exchange. I'm going to consider n as the nat. The length of the list is successor of n so that I can do L minus 1 inside. Okay, so n and d2. And finally, same values out of d2. And the winner, W. In this case, I'm going to have a wins by diag2 with B and W. So if I have the length of R is successor of n, then if I can extract the diag2 as D2, and I have all the same values out of this D2 as W, then W wins by diagonal 2. Let's test it. So we have wins by diag1. Let's also have a wins by diag2. So wins by diag2 is going to have this little board. So I'm going to have the first diagonal. So the code will not compile because I'm going to check the second diagonal now, so the cross one. So the compiler doesn't work. Wins by diag to BW. The BW is going to be R and RT. That's the big board. Okay. The code will still not compile because there's no given value that will satisfy this predicate. So let's wait for the compiler to search. It failed, and this is great. So this is intended. Let me put some zeros here, and I'm going to replace this one with X. Let me put a 0 here, and let's use an X here. And if I compile the code now, by virtue of diagonal 2, we should be getting a compiler green, which it does. All right, amazing. Now, you may have seen a little red in the code as we progressed with the entire implementation, but that's probably a bug in the IDE. So the code does compile. If I wanted to run this application, it would run. All right, so we have process finished with exit code 0, so the code compiled successfully. Okay, so we have all the predicates, all the possibilities. Wins by row, wins by column, wins by diag 1, wins by diag 2. Let me define a big trait. Let's call this wins. Then given a board, we have a winner as a player. And we have 4 given values. So I'm going to have given wins by row, which given a board, and W as a player, and using wins by row, B and W. I think that's what we call it here. So wins by, where's that? We have wins by column, and then we have wins by row. Okay, wins by row. So wins by row lets us create a wins with BW. Let's call this rows or row. Let me create a column. So I'm going to have wins by column here. Let me create another one for D1. So wins by diag 1. And again, I'm going to have a D2. Wins by diag 2. So diag 2. These are all the possibilities in which a player can win a particular board. So finally, let's do wins, and that's it. And let the compiler figure out what kind of type A is. So first of all, let's check if the code compiles, and it should, because the compiler can find the wins by diag 2 over X. So the code compiled just fine. But it would be really nice if we could somehow surface out the final type of A. And we have here under build.sbt, I have like a 20-line of code library from Rob Norris called typename, which simply surfaces out the type information from the compiler to the runtime. And this is pretty great. So I'm going to run a small function. So I'm going to say, I'm actually going to cut that out from main. So I'm going to say print type, given a type argument A, I'm going to have a value of type A, and I'm going to let the compiler figure out what the value and the type A will be. I'm going to say using type name as type name from that particular library. So I'm going to make sure I import that. So using type name as type name A. And this is going to be a string, and I'm going to have type name dot value. This is going to be a string, and I'm going to print that out. So print line, print type with A. That's pretty much it. So let's run the application and let's see how X won. Hopefully we'll get some type information to the runtime. So notice that we have a ginormous type, but this is just boilerplate. Let me replace this little token, the package name. So print type A, replace all with this little thing, and I'm going to replace that with the empty string. So let me run this again. Come on, compiler. I want to see the results. So notice that we have D2 here. So this is the given that's being used to summon this value. So we know for a fact that X won by diagonal 2. So not only do we know that X won, but we also know how X won. It won by diagonal 2. Let's do some more shuffling around. So I'm going to use x's here. X now wins by row, by the second row. If I run the application again, the type information is going to change. Let's see. Come on, compiler, compile my code. So notice that we now have the row type. The row was the one by which x won. So not only can we tell whether x won or not, but we can also tell the method by which x won the tic-tac-toe. I think that should rest my case. So there you have it, folks. I hope I managed to score a little point for Scala versus TypeScript in this type-level programming quote-unquote duel. I hope you liked this video and found it valuable. If you did, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this. Check me out on Twitter and LinkedIn. I post fresh updates on upcoming material. And check out my website at Rock the JVM. I have literally hundreds of hours of everything in the Scala ecosystem and more. Until next time, I'm Daniel, signing off.